Hello and welcome back to Thermo Shorts. We've been talking about open systems, namely about conservation of mass, but today we're going to broaden our perspective to look at how we do the first law of thermodynamics for these same open systems. So we've answered the question, how do we draw the control volume? We now know what happens to the mass, so we need to know for these open systems what happens to the energy. Now for closed systems, we used this version of the first law. We could take this same version, divide all the terms by delta t, and take the limit as it goes to 0, and we could get a rate equation for a closed system. And this would be the first step that we take as we're looking at these open systems, but we also have to remember that energy comes in and out with the mass, so we have to account for that as well. So now we're going to have this rate version of the first law for open systems. Notice the first three terms look like they did in the closed system rate equation, but now we have some terms talking about the mass flow rate times the pressure times the volume, and then we also have this delta E dot term. So what's the rate of change of energy from the mass coming in and the mass going out? So how do I work those out? We remember that this energy is really a sum of different kinds of energy, like internal, kinetic, and gravitational potential energy. So I put those into my equation. Now I can see that there are some terms, circled in red, that are multiplied by m dot in, and some terms circled in green that are multiplied by m dot e or m dot out. So I can collect like terms here and I get this equation. Now I remember that by definition, specific enthalpy is specific internal energy plus pressure times specific volume. So I can simplify this equation to look like this. Now this will be the rate version of conservation of energy, or the first law, for open systems. Now, if I'm at steady state, I want to know about the rate at which energy is being stored or depleted in my system, but at steady state, this is 0. So oftentimes, this term will be 0. If we're dealing with imperial units, things are always a little bit trickier. In this case, first, we have to divide by GC just to get the quantity right. All of these terms will be energy per unit mass. So H, if I look it up, is BTU per pound mass. But here, if I do this and my velocity is in feet per second, this term is only foot-pounds per pound mass. So then I'll have to change from foot-pounds to BTU. So the first thing is I got to remember to divide by GC. But then I also have to remember that the units are going to be a little bit tricky in imperial units, but in metric as well. So we have several different open system components that we'll use throughout this course. Turbines, pumps, valves, nozzles and diffusers, and heat exchangers. So I'll go through quickly an analysis of each one of these components. So for nozzles and diffusers, we're changing enthalpy into kinetic energy, or vice versa. Here, I look at my first law, I make a series of assumptions, and I get that 0 at steady state is equal to H in minus H out plus V in squared minus V out squared over 2. Now this is true in metric. If this was imperial, I'd have to divide by GC, and I always want to check my units. If I'm thinking about turbines, what I'm doing is I'm taking enthalpy in the fluid and turning that into mechanical work. So again, I'll make a series of assumptions, and I'll typically get that the power generated by a turbine is the mass flow rate times H in minus H out. For compressors and pumps, my assumptions here are actually the same, and I get the same equation as I did for turbines. But for turbines, I'm producing power, so the power is positive. For pumps, I'm consuming power, so the power is negative. If I'm dealing with heat exchangers, there's a couple of things that I can do, but one of them will be to make all of these assumptions. It's a little tricky to think that a heat exchanger is adiabatic. But what this really means is that all of my heat from my hot side of the heat exchanger is going into the cold side of the heat exchanger, and none of the heat is lost to the environment. In this case, I get this equation for the first law. Sometimes we'll talk about throttling valves or throttling devices. Here, they're a little bit like turbines in that they drop the pressure of the fluid, but they do it in a way that's isenthalpic, so that the change in specific enthalpy is zero. And we can get that from the first law. Here, I make several assumptions from the first law, and I find that H in is equal to H out. So, hopefully this is a good primer on what the first law for open systems looks like, and how we go about solving the first law for all of these different components by starting with the whole first law, making assumptions, and then getting to a specific equation for the case that we're looking at. Remember that all of these cases are general cases with assumptions that we usually make. That's different than saying assumptions we make every single time. Thanks for joining me on Thermal Shorts. I'll see you next time.